let's talk about Le Châtelier's principle. Le Châtelier basically figured out that if you disturb an equilibrium, a system that is at an equilibrium, the system will adjust itself to reach an equilibrium. You need to know and be able to apply his concept or his principle. You should be able to explain the relative equilibrium quantities of reactants and products and how these shifts will change and what changes will occur if we change concentrations of reactants or products, if we change the pressure or volume of the system, if we change the temperature of the system, if the presence or absence of a catalyst, and know how the change in equilibrium constant with the change in temperature is related to the enthalpy change in the reaction. So pulling enthalpy back in from first semester as well. So Le Châtelier, people say his name a little bit differently, but Le Châtelier's principle: if a system at equilibrium is disturbed by changes in concentration, pressure, or temperature, the system will respond by shifting its equilibrium position in a direction that will counteract the disturbance. The best way I can see this, not in a chemical world, is my cat loves to cuddle. And so if she's cuddling on me, like if I'm laying on the couch, she will cut, and I put a blanket on my legs, she'll immediately get inside the blankets and cuddle between my legs. I can lay there for a little bit, but then I get, I need to move. I can't lay there forever like she could, and so I'll move. I have disturbed her equilibrium. When I move, she will readjust to be able to stay where she wants to be. She wants to be against me. She wants to be cuddling, but she will readjust herself to be comfortable again after the move I've made. So we had reached an equilibrium. We had reached a steady state where she was comfortable, I was comfortable. I then move. Now she adjusts until she finds a new steady state or a new comfortable spot for her to be as well on top of me. Now put that into a chemical context. We have a reaction going where the forward rate and the reverse rate are happening at the exact same time. So at the molecular level, the reaction is still occurring constantly. But from a bird's eye view, we don't see a change anymore. Everything looks like it's just constant. Why is it still changing at a molecular level if we've reached an equilibrium? Well, honestly, these things have energy. And if we've taught you anything in chemistry, I hope it's that it wants to minimize its energy. The system will do anything it can to minimize energy. So it's going to keep moving because it's just dissipating its energy that way. But it's reached an equilibrium, so overall the rates are going to be the same. We won't see a change from the bird's eye view. If I do anything to disturb that equilibrium, concentration change, pressure change, temperature change, the system will shift to reach a new equilibrium that will counter the disturbance I made. Common stresses include change in concentration, change in temperature, change in volume or pressure, and the addition of a catalyst or inert compound. So, change in concentration. If I change the concentration of a reactant or product present, it will change your equilibrium. It will shift your equilibrium. If I change the temperature, we actually affect K this way. If I change the volume or pressure, if gases are present, depending on which gases I'm using and which gases I add to the system, it can change my equilibrium. There are situations where it will not have an effect. And now the addition of a catalyst inert, that word's hard for me, inert compound, even if it's a gas, have no effect on our overall equilibrium. You learn about catalysts and kinetics. Catalysts will basically find a different pathway and speed up the reaction by finding a different pathway for it to occur. Catalysts themselves do not affect the equilibrium rate of these reactions. They just affect how fast it gets to the equilibrium. So adding a catalyst isn't going to affect the equilibrium. And adding an inert compound is not going to affect the equilibrium either. So let's talk about some of these. So for temperature effects, I want you to think of an endothermic reaction as reactants plus heat plus products. Remember, endothermic means that heat is absorbed by the system from the surroundings. If you think about it that way, the system is absorbing that heat, and that's allowing the reaction to go forward. It's like we're treating heat as a reactant. So if you see an endothermic reaction, remember endothermic, delta H is positive, or delta H greater than 0, or I say endothermic, or the reaction is cool to touch. All of these mean endothermic. If I tell you the reaction is endothermic, if I say the reaction is cold to touch, if I say delta H is positive, or if I give you a value and it's greater than 0, then you know it's an endothermic reaction. At that point, I want you to write heat in as one of your reactants. Now, let's think about this. If we've got heat as a reactant, in which direction does the equilibrium shift if the temperature is increased? If I increase the temperature, I'm adding more heat to my reaction. I've added more heat to the reaction, which is adding reactant to the reaction. It's going to shift the reaction towards the products. It needs to do something to counteract what you did. You added more heat. It needs to get rid of that heat. So how does it do that? It reacts more of its reactant and forms more product to counteract that increase in temperature. In which direction does the equilibrium shift if the temperature is decreased? Well, in this case, I removed heat. I took heat away from the reaction. The reaction needs a set amount of heat at that equilibrium, and I just removed some of it. What it's going to do is it's going to pull that reaction back to form more reactant. If it forms more reactant, it's going to generate more heat as well. What about Kc? What happens to Kc if the temperature is increased? Kc is temperature dependent. If the Kc is increased, if the temperature is increased, so let's think about this in parts. If the temperature is increased, that means temperature is increased, okay? We've just established that if I increase the temperature, I'm going to form more product. So my concentration of products is increasing. In order to do that, my concentration of reactants must decrease, right? Because it's equilibrium. I'm not adding more things other than just heat here. I'm not adding more of the other reactants. And that heat has to react. It has to get rid of that heat, it has to dissipate it. It's going to do so by making more products. More products, less reactant. My numerator is bigger. My denominator is smaller. This is going to be a bigger number than it once was. So if the temp is increased, Kc is increased. Temp increases, product formation increases, Kc increases. And then we see the opposite effect if the Kc, if the temperature is decreased. If I decrease the temperature, that's going to pull the reaction back towards the reactant side. So your concentration of your products is going to decrease. Concentration of reactants is going to increase. Kc is going to be a smaller number. So Kc is temperature dependent. What if the reaction is exothermic? Remember, exothermic means heat has been generated. Heat is released by the system to the surroundings. Delta H is less than 0. Delta H is a negative value. I could also say the system is hot to touch. All of these mean it's exothermic. When you have an exothermic reaction, I want you to think about the reaction as reactants in equilibrium with products plus heat, and heat here is a product. So before we saw heat as a reactant, now heat is a product. Because the system is losing heat to the surroundings, it is generating heat as a product. With that in mind, let's look through the same things we just discussed. In which direction does the equilibrium shift if the temperature is increased? If I increase the temperature on an exothermic reaction, this throws students off. It's already hot. What is increasing the temperature going to do? It's an equilibrium. If I increase the temperature, it's going to throw the reaction back towards making more of the reactant. It's going to shift the reaction to the left. What if I lower the temperature? If I decrease the temperature, well, now I'm taking away a product. I'm cooling the system down. The reactant's going to go towards the right to produce more product. What happens if to Kc if the temperature is increased? Well, remember what Kc, you got your products over your reactants. If I increase the temperature, my concentration of products will decrease. My concentration of reactants will increase. So Kc becomes smaller. And what happens to Kc if the temperature is decreased? Same thing, or same concept here. Kc is equal to the concentration of your products over the concentration of reactants. If I decrease the temperature, I'm going to increase product, decrease reactant, and Kc becomes larger. We take advantage of Châtelier's principle all the time in equilibrium, in lab, in different systems. And so I need you guys to think about this actively, because you're going to see it in examples, you're going to see it in lab, you're going to see it in class. What are we doing? We're taking advantage of the fact that we were at an equilibrium and we're somehow manipulating the reaction to cause a change we want. Two more principles we need to cover. Compressing a gas and addition of a non-participating substance. So compressing a gas, if I take a gas and I compress it, it favors the side with fewer moles of gas. So for example, if I had the reaction N2 plus 3 moles of H2 in equilibrium with 2 moles of NH3. And that's what I see here. Increasing the pressure, decreasing the pressure. If I increase the pressure, it's going to favor the side that has fewer gas molecules because there's just less space for all of them. So increasing the pressure, the reaction is going to shift to the right where I only have 2 moles of gas. So I have 4 mole on the reactant side and 2 mole on the product side. Increasing the pressure, I see that I'm going to favor the side with fewer moles of gas. Decreasing the pressure, I see the opposite effect. It's going to favor the side with more moles of gas because they just have more space. So compression of a gas favors the side with fewer gas molecules. Decompressing a gas favors the side with more moles of gas. And that's because your Kp is equal to the partial pressures of these individual gas species. Now, the one that throws students off is addition of a non-participating substance or a catalyst does not affect your equilibrium position. The catalyst, most students are fine with because catalysts do find just a faster pathway to reach your ending point, which in this case is an equilibrium. But non-participating substance, this could be a gas. If I added helium gas to this here, it would have no effect. It's not going to affect the equilibrium because it's not participating in the system itself. Does it add more gas molecules? Sure. But this equilibrium is based on the partial pressures of the reactants and products in the equilibrium. Addition of helium doesn't affect the individual partial pressures comparative to one another. Does it affect the partial pressures of the overall system? Sure, there's more gas particles, but the ratio of these species to one another does not change. Therefore, adding a non-participating substance such as helium gas does not have an effect on your reaction. Consider the following reaction. I've got N2 gas plus 3 moles of H2 gas giving me 2 moles of NH3 gas. And I'm told the delta H of this reaction is negative 92.4 kilojoules. This right here tells me a lot of information. The fact that this is negative tells me this is an exothermic reaction. Remember, exo, delta H is negative, endo, delta H is positive. Because it's exothermic, I'm going to write plus heat on my reaction. And I'm going to write it as a product because it's exothermic. Now it's going to be easier to answer these questions. What happens if I increase the concentration of N2? I increase the concentration here, the reaction's going to go to the right, more product formation. Because it's always going to adjust to whatever change you've made. What if I increase the concentration of NH3 in the system? It's going to shift the reaction to the left. What if I decrease the concentration of NH3? It's going to shift the reaction to the right and form more product. What if the total pressure is increased by compressing the system? Well, I have 4 moles here and 2 moles here. If I compress it, it's going to go to the side that has fewer gas molecules. So it's going to shift to product. What if the total pressure is increased by the addition of helium? Helium is a gas, but helium is also non-participating. So no change. What if I increase the temperature? It's an exothermic reaction. I increase the temperature. It's going to move back towards reactant formation. What if I decrease the temperature? I've taken away a product. It's going to have product formation. And what if I add a catalyst? No change. So we take advantage of this in lab itself. There's a lab that you're going to do in organic. If you take organic here, you're going to do a lab where it's an equilibrium system. We're going to do a couple labs, so there's an equilibrium system. And so for one lab, we remove a product while the reaction goes. If I'm constantly boiling off a product and removing it from the overall system, then I'm decreasing the concentration of one product, and I'm encouraging the reaction to continue forward in the forward direction. There's all kinds of ways to manipulate these things, and I need you guys to actively think about how does that work. Let's work another example. Consider the following system in equilibrium. Nickel oxide solid plus CO2 gas in equilibrium with nickel solid plus CO2 gas. CO gas is a reactant, CO2 gas is a product. I'm sorry, I think I said CO2 in the first place. And it says delta H is a negative value. Negative value means that it's exothermic. So it is plus heat. on the product side. I increase the temperature. If I increase the temperature and it's an exothermic reaction, it's going to form more reactant. The pressure of CO2 is increased. I increase the pressure of CO2. This is the partial pressure of CO2, which means I'm also in effect increasing the concentration of CO2, which means I'm increasing a product and more reactant will be formed. I decrease the pressure of CO, which is the partial pressure of CO. Increase. Sorry. I can read. I increase the pressure of CO, which is the partial pressure of CO, which in fact means I increase the concentration of CO. It's going to push it to more product formation. The mass of NiO is increased. I'm increasing the mass of nickel oxide, but nickel oxide is a solid. This will have no change. Nickel oxide is a solid. It's in equilibrium, so if anything, we need more CO2 or CO to react. But affecting a solid, no change. The total pressure of the system is increased by addition of helium gas. Helium gas is non-participating. No change. The total pressure of the system is increased by compressing the system. Well, over here, I've got 1 mole of gas. Over here, 1 mole of gas. So even though compression should affect the system, in this case, there's no change. Because I have 1 mole of gas on each side. Kp is equal to the partial pressure of CO2 divided by the partial pressure of CO. It's going to stay constant regardless if I increase or decrease the pressure because I have 1 mole of each species on either side. And our last example, CO2 gas, or CO gas, so he's saying CO2. CO gas reacts with 2 moles of H2 gas to produce 1 mole of CH3OH. It tells me the delta H value here is negative 90.7 kilojoules, which is exothermic. Which means plus heat. So what will happen to the equilibrium concentration of methanol specifically? This is methanol. So in this case, I want to know what's going to happen to methanol specifically if I do the following. If I increase the partial pressure of CO2, methanol concentration, MEOH is a shorthand, will be increased. If I decrease the partial pressure of H2, methanol concentration will decrease because I'm going to have to make more H2 to reestablish an equilibrium. The total pressure is increased by the addition of helium gas. Again, non-participating. No effect. The reaction mixture itself is compressed. On this side, I have 3 moles of gas. This side, I have 1 mole of gas. If I compress this system, then it's going to go to the side that has less gas particles. So the reaction mixture is compressed. The methanol concentration will increase because it's the side with fewer moles of gas. I increase the temperature. This is an exothermic reaction, so if I increase the temperature, it's going to push the reaction back towards reactant formation, and my methanol concentration will be decreased. And a catalyst is added. Catalyst will have no effect.